about work that I did with Thomas Vidic and Victor Albert about group Coset Monogamy Games and an application to device-independent QKD. So the name's a bit of a mouthful, but I'll sort of go through it, essentially word by word, and hopefully have a better idea what's going on there by the end of the talk. So first, start with a bit of motivation for why we're doing this, and that needs a little bit of group representation theory. So what we're working with is Hilbert spaces that are the function spaces on some group, and this naturally represents a lot of interesting physical spaces that people are interested in. For example, qubits, that's just the group of n bits under addition, or under XOR addition. There's the group of rotational symmetries, or different groups of rotational symmetries correspond to physical objects that have some kind of, or like the rotational states of physical objects. And this is a nice picture that I sort of unceremoniously stole from one of the papers of my collaborators, a paper of Albert, Covey, and Preskill. And the other sort of, another sort of group space that people are interested in is just the vector space Rn under addition. And that corresponds to optical modes, which people have been talking about all week. So given this group structure, you can build states on this space, at least mathematically, that exploit the structure in potentially useful ways. And this is the idea of these coset states. So the beginning point of this is that you take a subgroup of your group and you look at a superposition of all the elements of the subgroup, and that's a valid state on the group as long as it's finite. And that's quite an interesting object, but we can expand on this and get a whole basis of the space based on this one subgroup. So you need to get a bunch of orthogonal states that are sort of orthogonal in a useful way. And one way to do it is consider cosets of the subgroup. So you look at shifts of this state by other elements of the underlying group that are not contained in the subgroup, and that gives orthogonal states because the cosets partition the group. And then this gives us an orthonormal set of states, but it's not the full orthonormal basis because it's not yet complete. And to complete it, we can add phases in front of these group basis elements, and these phases are given by irreducible representations. So just functions from the subgroup to some so unitaries that preserve the group structure, unitaries of some dimension, and the irreducibility is not super important, but it gives orthogonality properties. And if the group is abelian, then the full representations can be used, but if not, the irreducible representations are not one-dimensional, so we need to concentrate on matrix elements. Luckily, there's very nice results from representation theory, notably the Schur orthogonality relations, that tell us that directly imply that states of this form are in fact orthonormal, and that they form an orthonormal basis of this group space spanning over the cosets of the subgroup and the matrix elements of a particular fixed set of fixed and complete set of irreducible representations. These coset states have been used in a few places, notably in error-correcting codes. And I'll give a couple of examples just as a motivation. First, there's the sort of quintessential example of a quantum error-correcting code, is the CSS code. And the code words there are built from coset states on the n-qubit space. And if you were at James Bartosek's tutorial talk earlier in the week, these are the coset states that he was interested in. Next, we can go to more or stranger examples. The GKP states are also a state that's constructed from or it's also an example of a coset state. But here the subgroup is the integers as an additive subgroup of the real numbers. Next, molecular codes are built from subgroups of rotation groups, and this is something that was previously studied by in the paper of Albert, Covey, and Preskill. And there's also a code related to the Coset states of optical modes, and these are the analog CSS codes, because they really are like an analog continuous variable variant of the CSS code states. And here the code words are sort of like they are well approximated by squeeze states, and in fact is nice. However, if you go and you construct the states, you take the sum over the elements of the subgroup and replace it with a Hauer integral, for example, you end up with something that objects that look like this. They're sort of superpositions over a very small, sort of measure zero subset of the group space, and that's not good because that's not a nice function. So you can end up with states that can't be normalized and don't really sit in the actual sort of mathematically rigorous state space of the group. The way to deal with that usually is by some kind of damping procedure. And that's sort of this is supposed to illustrate what it does. And you sort of squish away the infinities by replacing anytime there's an infinite Dirac delta type normalized thing, you replace it with a Gaussian that sort of in the limit would tend in distribution to the Dirac delta. And this works. You get states. But it's harder to work with because you lose the nice orthogonality property of the Coset states that you would have had for a finite group. Luckily, there is a way to go around this, and it uses some very fun mathematics. It's that instead of just generalizing the set of states into some that form the basis, it's possible to generalize only measurement in the basis. So formally how this is interpreted is by means of something called an operator valued measure. That's a function that every subset of the sort of index set for this measurement associates an operator, a positive operator, and that positive operator corresponds to the probability of making a measurement within that index set. Sort of in terms of this non-normalized Coset state that you get directly from the definition, you end up with this expression, sort of intuitively, that it really is sort of the projector onto the Coset state, the non-normalized projector onto the Coset state, averaged over this set of indices, some set of indices, and then you end up with an actual projector onto some subset of these indices. And this allows us to preserve the orthogonality of the Coset states and make it possible to work with it more or make it possible to work with objects, these Coset state-like objects more easily because there is this orthogonality of the projectors. An example is for the case of optical modes. The state, the sort of damped state version are squeeze states, and the this operator value measure version ends up being homodyne detection. So now the next question we can ask is what can we do with these objects? And one of the things we can do is something called the monogamy entanglement game. This is a scenario that's supposed to quantify some aspect of the no-cloning principle that says that quantum states cannot be exactly copied by a quantum operation. So the idea of a Coset state game comes from a paper of Colangelo, Liu, and Jandry, where they use it to do a variety of cryptographic tasks. And they work with a Coset state game that that is on these Coset states for the space of n bits. But it's possible to generalize this quite directly to Coset states on an arbitrary group. How this game is constructed is it's a 3-player game. There's Alice, Bob, and Charlie. Alice is a an honest referee, and Bob and Charlie are potentially dishonest players, but they all hold some quantum system. Alice holds a quantum system given by the state space of a group, and Bob and Charlie hold arbitrary systems. And the game begins by Bob and Charlie preparing a shared state that is shared among all 3 players. Next, Alice samples some subgroup of the group and measures according to this Coset operator measure, this operator value measure for the Coset states of the group, and gets some pair of answers, a coset and a matrix element of an irreducible representation. Next, this is all done without Bob and Charlie knowing which subgroup, Alice chose. But after, in the next step, she does in fact send the subgroup to Bob and Charlie. After which, however, they are no longer able to communicate. Finally, Bob and Charlie try to guess aspects of Alice's measurement using some arbitrary measurements on their spaces. Bob is trying to guess the Coset representative. Charlie is trying to guess the matrix element. And the idea is that they win if their guesses are correct up to some error tolerance. So here, what's interesting is that although heuristically the fact that the winning probability of this game is not 1 is based on the no-cloning theorem. Bob and Charlie are actually guessing different pieces of information, and in some way they're sort of inextricably linked within the state, so they cannot be separated between the 2 players. Using some similar techniques to what's been previously studied for monogamy entanglement games, we're able to find a bound on this winning probability, and it looks like this in the general case, and it's related to the measures, so the harm measures of overlaps of different copies of subgroups, and this expression is kind of unparsable in this form, but in many cases, what's nice is that it ends up giving an exponentially small winning probability in some sort of size parameter of the group. Say, for example, for something like Rn, it would be a winning probability that's exponentially small in n. So that's a quite powerful tool to do things with. And before I do something with it, I would also like to tell you about a different form of this game that's almost equivalent. Here, the same players, but they're set up in a different geometrical arrangement, and the game, this other form of the game proceeds as follows. First, Alice, instead of measuring she prepares a state, and since she's preparing states, she has to prepare one of these damped Coset states, and then she sends that state into the world, and there's some kind of pirate channel that does some operation and splits it between Bob and Charlie's Hilbert spaces, and potentially in a very entangled manner. But in any case, it ends up at the end with Bob and Charlie holding this shared state constructed from the state Alice sent. Afterwards, Bob and Charlie no longer communicate; they're assumed to be isolated from each other. And Alice, similarly to the original form of the monogamy entanglement game, sends both of them the information about the subgroup she chose, and they try to make the same guesses. Bob tries to guess the coset, and Charlie tries to guess the matrix element of the representation. And what it turns out that using a simple transformation related to the Troyer-Minkowski representation of this channel, it's possible to show that the same bound on the winning probability of the game actually holds. And I'm running a little bit over time, so I think I need another minute or so. And this form of the game is actually useful because, or perhaps more useful because it sort of models sending states into the world that some kind of cryptographic properties can be shown, for which some cryptographic properties can be shown. And one of these applications is one-sided device-independent quantum key distribution. This was one of the original applications of a monogamy entanglement game, and the idea is you take this scenario. You have Alice and Bob as the sender and the receiver in the QKD system, respectively. And the third player, Charlie, as well as this sort of pirating channel, would represent the eavesdropper. And then the fact that the winning probability is low for this game would imply security of the QKD protocol. That's on one, and then that was shown by Thomas Schopper and Jens Boehner in 2013 to give some kind of device-independent QKD for the version of the BB84 protocol. On the other hand, because we can work now with independent dimensional group spaces, we can think about continuous variable states and how they can be used in QKD. By putting these two together, we should get continuous variable one-sided device-independent QKD, and that's in fact what we do get. And the example we work out is using optical modes. So here the Coset states are products of squeeze states in either the position or the moment, sort of aligned along the position or the momentum direction. And the measurement in the Coset state basis is, as mentioned, Hamadan detection, and it actually does work out that this can give a secure QKD. However, in the current form that we have, there's still quite a low error tolerance. But it's a sort of proof of principle construction of device independence per continuous variable QKD. To finish the talk, I'd like to mention a couple of open questions. As I just said, there's definitely avenues to take this QKD construction and make it more practical by, say, increasing the error tolerance. And another direction is that this is QKD with squeeze states, and the more popular and more practical version of continuous variable QKD is using coherent states. And perhaps it's possible to use these monogamy entanglement techniques to show some kind of device independence for coherent state QKD protocols. And that brings me to the end of my talk. Thanks for listening, and I'll open the questions.
Thanks for the nice talk, Eric. Are there any questions?
Hello. Sorry, just slightly confused. if we want to do DI QKD with this, does it matter that the underlying states are continuous variable? I thought we would just need the discretized outputs after,
I think it does matter. Maybe there's a different way to do it that just takes the continuous variable state, discretizes the output, and then adds on some device independence. But at least in the way I've seen it, right, this one-sided device independence was based on this monogamy entanglement property that had only previously been known for BBD4 and BBD4-like states. And here there's a sort of this monogamy property for a different family of states that sort of gives this continuous variable version.
Because from the DI perspective, I think the way we would usually view it is that there's some measurement on some infinite dimensional or unbounded dimensional space, and we get a discrete set of outputs, and we sort of don't care about the structure of the underlying space. So,
I think definitely for like fully device independent QKD, this would perhaps not matter because you're you're essentially doing some kind of self-testing to certify that within your infinite dimensional space, there sits a finite dimensional space that looks like a PPR bit, right? But here, since it's one-sided, it sort of depends more on the actual underlying state structure.
Okay. So you mean one-sided DI?
Yeah.
Okay. Thanks. Yeah. Sorry.
Thanks for the question.
Are there more questions? Over there's one.
Hi, thanks for the talk. So as I understand, this is sort of a game where quantum does worse than what you could do classically. Is that correct? So classically, you can clone these things, and because you showed there was an upper bound on the winning probability in quantum.
Yeah.
So is there like an intuition as to like how this gives you security?
Yeah, because I mean the style of game is something that you could definitely, if everybody was classical, it would sort of be trivial, right? But this actual game can't be played without quantum players, right? Because even the referee has to be quantum. And sort of the idea of a bound on this game is essentially saying that it's sorry, I lost my train of thought. It's saying that that sort of dishonest quantum players can't do well because who has to do the best winning probability would be sort of a winning probability of one player sort of is if that's high, that's to the detriment of the other player. Which is sort of how these monogamy entanglement relations are usually interpreted.
Great, thanks.
Eric?
Yeah.
So you said like the initial motivation for the monogamy entanglement game came from the Polarangelo paper. So have you thought in other directions to extend this game to help more in this direction, especially like unfoldable encryption, copy protection kind of stuff, where like other extensions of monogamy?
Well, I mean, it would need this family of games with like on infinite group spaces, these infinite dimensional Coset states. I don't think we'd have to use different techniques to extend it to something like unclonable encryption, because we're still using the technique of Thomas Schelper, Kanievsky, and Wiener, which has a fundamental limit to how well it can how low of a winning probability it can guarantee for something like unclonable encryption. I mean, maybe there's a way to exploit the infinite dimensional nature somehow, but for the moment, I don't see it.
Yeah, my question was not extending it in the infinite dimensional way, but the game itself, like other kinds of extensions that might help in like unclonable encryption kind of stuff. Not exactly to extend it to infinite, so not that way it's work, but like you take the original monogamy.
Oh, okay, yeah, I'm sure it's possible, but I don't know. I don't know how I go about doing that. Thank you. Thanks.
All right, in the interest of time, I suggest that we move on to the next speaker. So let's thank Eric again for the talk.